Hey everybody, today is a very special moment for you all because you all are going to learn the fundamental theorem of calculus, part 1 at least. There are 2 parts to it, so we'll do part 1 today. We've been leading up to this for the past week or 2. I've been hinting at it, but today is finally the day you're going to learn it. So go to the next spot in your notes, title it as Fundamental Theorem of Calculus. Again, this is a very, very important video, so I cannot emphasize enough, no muting the video. Okay, there we go. So slide 1-4. Again, fundamental theorem of calculus is one of the most important named theorems in calculus. That's why they call it the fundamental one. We're going to explore 2 different graphs because we're going to try and discover the theorem for ourselves. I'm not just going to tell it to you and have you memorize it. I want you to see how it comes about. So why don't you pause the video right now and draw this just so you can see why we even need this fundamental theorem of calculus. Now, what we did in class today, you had the period to work on that worksheet. You already found things like this. The reason you were able to do this is because you could use geometry. Because this means find the exact signed area. So no more estimating or approximating with rectangles and trapezoids, the exact area. Again, geometry saved us here. We were able to get the exact signed area. Not every function looks like this, where you can use geometry formulas. Some functions are curvy, or a lot of functions, I should say, and there's no geometry formula for these shapes here. So now let's have the same exact question as right here, but now we want it for this function. There is a signed area, but notice these are not just normal geometry shapes that we could use formulas for. We still need the exact area. But because there's an integral sign here, remember that's taking the place of the limit as n goes to infinity of, 1, infinitely many rectangles or trapezoids. So we're not going to sit here and try and draw infinitely many because that's impossible. So it seems like we have a major dilemma here and we're stuck because we can't do infinitely many. We can't get it perfect. But let's go try 2 examples and explore to try and see if we can figure out another way to do this. Now, we're going to do an example where we could use geometry, and that will lead us to examples where we wouldn't be able to do geometry. So here's our first example. Now, what I want you to do is, again, pause the video, write down the example, and draw a good picture of this. Don't make it sloppy. And you can go ahead and draw all this stuff right here, and then you can press play again and listen to what I say and add comments. So our function is 1/2 x plus 1, linear function, and I want this. Now, if I replace f of x with what f of x is, I could write this. These are the exact same thing. I'm just replacing f of x with the function itself. And this means that I want the exact area under the curve, so from the curve to the x-axis. And again, this means I'm doing infinitely many rectangles. But the thing is, I don't need rectangles here because I can do it exactly. And right here, sorry, I cut off a tiny bit right there. All right, so I want this shaded region. Notice my lower limit of integration is 2, my upper limit of integration is 8, and I want this blue region here. So let's go ahead and do geometry because geometry can save us here. I'm redrawing the shape. One of my bases is 2, one of my bases is 5. Remember, the bases are going up, they're parallel. I'm averaging my bases, multiplying by the width, which is from 2 to 8, so 6, and I get 21. So 21 is the exact area of this blue region. So we could stop right now and say, okay, well, geometry saved us again, but let's try doing something else. Notice that right here, I had an integral, and I was specifying from 2 to 8. So it was, we're going to talk about this more later. It's a definite integral from 2 to 8. I gave you lower and upper limits. Let's forget about the 2 to 8, and let's just rewrite it like this. So no lower and upper limits. This just means find the antiderivative. That was at the end of the worksheet you did today. So if you see no upper and lower limits, just find the antiderivative. So let's replace f of x with what f of x is. And again, let's just find the antiderivative, and let's see what happens. So antiderivative, I'm adding 1 to 1. I'm dividing by my new exponent. 1 becomes x, I add c, and by now you should be okay doing antiderivatives. When you copy this down, make sure you're following along. And now, just for the heck of it, let's try something else. Let's take our antiderivative, whoops, which is right here, and let's evaluate it at our endpoints. So 8 and 2. So we're still kind of exploring here, building up to it. And the reason I got 2 and 8 is because they are the endpoints here. So I'm going to plug 2 and 8 right into here. So whenever you do this, follow along with the math. Don't just blindly copy it. Make sure you realize what I'm doing. I'm evaluating my antiderivative at the upper point and the lower point, and I'm getting these two numbers. And now, we're again still exploring here. Let's try subtracting them and see what happens. If you subtract the upper limits values from the lower limits value, so 24 plus c minus 3 plus c's, distribute this minus here. Notice my c's cancel. Oh, 24 minus 3, that's 21. That should sound familiar because I had 21 here and here. So when I got the exact area, it was 21. When I found the antiderivative, evaluated it at the endpoints and subtracted, I also got 21. That's kind of cool. So let's see if that was just a coincidence or if it might hold for all of them. Let's try another example. Second one. This is the only other one we'll do. So I want you to pause the video again and copy down everything you see on the screen. Make your picture neat here. Shade in. We want this function now, and we want the area, the exact signed area. Remember, exact signed area from 1 to 12. So pause the video. And once again, I'm going to replace f of x with what f of x actually is. So this means exact signed area. We, again, can use geometry to help us here. Geometry to the rescue. We don't have to worry about infinitely many rectangles or trapezoids. So I have this one here, and I have this one here. Remember, it's signed area. So 1/2 base height, 1/2 base height gives me these two heights. Or these two areas, sorry, signed areas, and when you add them, you get this number, 33 over 2. Let's do the same thing we did before when we were exploring and see if the same thing happens. So again, I'm going to want the antiderivative of this. So let me scoot up here. Whoop. Okay, so I just want the general antiderivative. I'm getting rid of the lower and upper limits, 1 and 12, just general antiderivative. So if f of x was negative x plus 8. Notice my notation here. Capital F of x. That means antiderivative. That was from a prior video, so if you forgot that, make sure you commit that to memory. Antiderivative. So I'm adding 1 to my exponent, dividing by it. 8 becomes 8x, and I have a plus c. Again, let's just try evaluating it at the endpoints, 1 and 12. I'm getting that from here. So f of 12, f of 1, so I'm plugging 12 in, and I get 24 plus c. I'm plugging 1 in. I'm getting 7.5 plus c. Let's try doing this guy minus this guy and see if a similar thing happens again. So let's subtract them, f of 12 minus f of 1. Distribute your negative. Oh, look, the c's cancel again. And what happens? Oh my God, we get 33 over 2 again. It's the same thing. So the exact area is the same as if you were to find the antiderivative, evaluate it at the endpoints here, and subtract them. This, drum roll, get the horns playing. This is a huge moment for you guys. Fundamental Theorem of Calculus, Part 1, FTC. F of x has to be continuous. Keep that in mind. We're on the interval a to b. This right here, to find the exact signed area under the curve, we take the antiderivative, we evaluate it at the endpoints, and we subtract, just like in the prior two examples. Now this right here is brand new notation. Calculus has a lot of new notation you're learning. When you see this, again, this is the antiderivative. Capital F is antiderivative. This just means take the antiderivative, evaluate it at the endpoints, and subtract. So when you see this, it really means this. So again, make sure you write this down so you remember f of x is the antiderivative. When you do the antiderivative, this is also important. You can just forget about the plus c right now, because we're going to have lower and upper limits. It's a definite integral, and the c's canceled anyway. In the previous two examples, they canceled. So put a big box around this, stars, hearts. We have some summary statements here. Okay, so to find the exact area under any continuous function, you evaluate and then subtract the antiderivative at the endpoints. Some vocab words, some technicalities here. This, when you calculate this whole thing, you are doing what's called integrating or doing integration. F of x, my function, is the integrand, and this right here is an integral. Now let me do one very quick example. These don't take very long, they're pretty quick. This is what we're going to spend Thursday on. We'll be practicing it. Let's say I want, oops, I forgot a dx. I want this. Now notice, before this video, you would have thought, okay, that means exact area under the curve from 1 to 4, so I want this, and now I'm going to have to draw infinitely many rectangles or trapezoids. Well, not anymore, because we have the fundamental theorem of calculus to the rescue. So what this means is I need the antiderivative from 1 to 4. So let's find the antiderivative. That's not too bad here. I add 1 to the exponent, divide by it. 2 becomes 2x. I don't need that plus c because the plus c would have canceled anyway. And I'm going from 1 to 4. So what you're going to do is first evaluate the antiderivative at 4. So go ahead and write this down with me as I do it. Subtract, now evaluate your antiderivative at 1. 1 cubed over 3 plus 2 times 1. So let me just emphasize one more time. This is the antiderivative. I'm plugging 4 into my antiderivative, which is this. I'm plugging 1, the lower limit, into my antiderivative, which is this. And then I subtract. So I don't have a calculator, so I did a ton of fraction work here. I end up getting with a fraction at the end. I'm just simplifying this, and I'm simplifying this. I got common denominators. I end up with 88 thirds here and 7 thirds here. Hopefully I didn't make a little arithmetic mistake. 81 thirds. Now remember, 81 thirds is this area exact under the curve. So if you were to draw infinitely many rectangles or trapezoids, you would get this exact area under the curve. So we'll practice this a lot next time I see you, and have a great night.